Hi everyone, welcome to the Nuclear Masterclass. My name is Christian Diget and I'm a nuclear physicist at the University of York. And for the past 2 weeks, you've been exploring some exciting, I think, nuclear physics from nuclear isotopes to neutron stars. And these are some of the nuclear physics topics that I'm particularly interested in my own research. Now, I hope you found those weeks very interesting and also challenging. And for the final 2 weeks now, we will be trying to use some of the same topics to go into two of the applied areas of nuclear physics that I find very interesting, but also challenging. And for this week, the topic, therefore, is nuclear fusion. And for this, I look forward to welcoming two researchers, Dr. Kate Lancaster, here from University of York, and Dr. Aneeqa Khan from University of Manchester. And these two will lead us on a journey toward fusion here on Earth. So during Kate and Aneeqa's presentations, do keep the questions coming into the webinar Q&A. You will be able to see your questions when I mark them as questions that I will try to get to answer. I appreciate that we will hopefully have many more questions coming in than we can answer, but if we can't answer them all, we will do our best to give some written answers in the week to come. So do keep the questions coming in for both Kate and Aneeqa as the webinar goes on. So first of all, welcome to you, Kate. Welcome to Kate Lancaster. Kate is researching. Yeah, welcome to you. It's good to see you, Kate.
Likewise.
So Kate is researching how to make fusion happen here on Earth by using massive lasers. And I think that's a fantastic topic. Who wouldn't want to use massive lasers to make fusion happen, right? So what Kate is doing with these lasers is trying to understand the interaction between the fusion plasma and the lasers that you try to make, well, heat up this plasma. But we can talk about that much more later as well. Today, Kate will give us also a broader overview of fusion and the different ways of making fusion happen as an energy source. So welcome to you, Kate. It's great to see you, and thank you so much for joining the masterclass. So before we get started on your particular topic, I wonder, how did you get into fusion in the first place?
Well, it was a bit of an accident, to be honest, because I don't think I ever dreamt as a 5-year-old I'd be working on nuclear fusion as a career.
Yeah.
Basically, me and my sister were the first people in my family to go to university, and I went to university to do physics. And it was during that time I did a placement year at the National Physical Laboratory, and I was just mucking around with optics during that placement, and I really enjoyed it. And by the end of the degree, I really liked basically playing around with lasers and optics and wanted a career to do with that. And so that's what brought me to the Rutherford Appleton Lab in Oxfordshire, to the Central Laser Facility, to specifically work on really high power lasers. And it turns out it's really hard to work on high power lasers without making this stuff called plasma, which I'm going to talk to you about, which is absolutely fundamental to nuclear fusion. And so it was a very sort of torturous path that led me to nuclear fusion. But I wouldn't look back now. It's been nearly 20 years and I'm still here. So
Right. That's great. That's exciting to hear. So I think that's a good presentation, introduction of yourself. Now, for a start, so maybe we should go straight into your presentation, and then we can get back with questions from the audience subsequent to that. So okay. Thank you so much. I'll hand over to you. Thank you.
Thank you so much. Okay. I'm here to talk about whether it's possible to build a star on Earth. And scientists like myself and Aneeqa have been on this journey now for a little while. Obviously, we haven't been on this journey since the start. It's been going on for a number of decades, and I'm not that old. But I'm going to be asking the question, is it possible to build a star on Earth? And then telling you a bit about how scientists are trying to go about that. So I like to, let's see, there we go. So the first thing I'd like to talk about is this picture, which I think really represents the problem that we have on Earth. This picture was taken from a hotel window when I went to a conference in Tokyo. So this is looking out over Yokohama, which basically into the distance kind of connects up with Tokyo diaspora and beyond. And you can see it's just energy use, energy use, energy use. And it shows that we're energy addicts. And our energy use is increasing and increasing. Our population is going to increase continuously, but the energy that we have available from conventional sources is actually decreasing. So at some point, unless we take action, there's going to be a shortfall between the energy that we need and the energy that we have. So that really sounds like quite bad news, doesn't it? But don't panic, because scientists like myself and Aneeqa have been working on this for a while, and so hopefully we'll come up with a solution which will give us a good baseline source of energy for the future. And it turns out that if you look out into our own dear universe and we look at the stars, they're actually powered by nuclear fusion, which is something that you heard about from Alison Laird last week. She talked about how the proton-proton chain basically works in stars, which effectively, if you look at it on a macro scale, is burning hydrogen and turning it into helium. But that process actually releases lots of energy. So this nuclear fusion, which is two light atoms coming together to make a heavier atom and some energy or whatever else, actually is a mechanism by which lots of heavier and heavier and heavier elements are actually produced in the center of stars. So it turns out all the atoms that make your body up were forged in the center of stars. So a nice thought for a Monday afternoon is that you're all made of stardust. Every single atom in you was forged somewhere in a star or in the universe. So stars are really good at producing energy. So how can we get a star, put it into a jar in miniature? And that's what this talk is all about. Is it even possible to do that? So what we're trying to do on Earth is we're trying to do the same sort of thing that we do in stars. So we're trying to turn hydrogen into helium. So in this sort of case, we're using two types of hydrogen, two isotopes of hydrogen. We're using deuterium and tritium. Now, deuterium is present in seawater in really rather large amounts. For every 6,000 hydrogens, there's one deuterium. So it's very, very abundant. Tritium, however, is not so abundant. So for every 10 to the 15 hydrogens, so that's 1 in 15 zeros, hydrogens, there's only one tritium. So it's not really naturally occurring. So you might think, Kate, you guys are stupid for basing an energy source on something where you don't have the fuel naturally occurring. But I will come back to that because it is possible for us to make the tritium. So let's try and understand how we get fusion to work on Earth. Right, so we take the deuterium and tritium and we give them lots of energy. They fuse together and they produce helium and a neutron. But where on earth does that energy come from? So as you can see on the screen, we've got the most famous equation in the world, I think, which is E equals mc squared. Now, E is energy, m is mass, and c is the speed of light squared. And the speed of light is an extremely large number. It's 3 times 10 to the 8 meters per second. So c squared is a very big number. And Einstein said that the speed of light is constant, wherever you look, wherever reference frame you're in. And so for the purposes of this equation, what that tells us is if c squared here is a constant, then energy and mass are somehow interchangeable. We can change one into the other. And that's fundamental to how we get energy out of fusion. So if we think about what that means in reality, we've got our deuterium and tritium, and if we add those masses together, give them energy, they fuse, and then we get the resultant particles, and then we add those masses together, we'll see that there's been a mass loss between the first and the second situation. So we take that tiny little value of mass that went missing, times it by c squared, and what you get is a huge amount of energy. So it's a really efficient way of getting energy out. Now, let's get back to this problem of tritium. So the neutron here carries away most of the kinetic energy of the interaction, so this moving energy. And it turns out if we can surround our reactor with lithium, which is really abundant in the Earth's crust, it's what you have your laptop batteries made of, then the lithium can actually capture the neutron and make tritium. So provided we can make enough tritium in that process, then we should be okay, which is good. Now, it being very energy efficient is one of the most fundamental reasons why people have been working on fusion for such a long time. If you look at the chemical energy contained from burning 40 tons of coal, it's the equivalent of the deuterium, so the fusion energy that you can get from the deuterium in half a bath full of seawater and the lithium in a laptop battery, because I said you need lithium for fusion to work. So that's a really small amount of fuel. And actually, this half a bath full of seawater and the lithium in a laptop battery is one of your lifetime's energy needs. Done. So that's all the fuel you'll need for basically the rest of your life. So that's really exciting. So it's one of the reasons why, even though fusion is really hard to do, scientists on Earth have been trying for a very long time to get it to work. So it's very attractive. Now, that's not the only reason why we want fusion to work as well. There are other advantages as well. So if you think about how a conventional fission power station works, you take a big atom and you split it up into smaller parts. And unfortunately, this process creates long-lived radioactive waste. Now, of course, these fission power stations have got better over time and they're much more efficient. And I'm not against fission, actually. I think it's a good stopgap until we have fusion. But unfortunately, there is a long-lived radioactive waste burden on future generations. Now, fusion doesn't do that. Fusion produces helium, right? Now, it does produce a neutron, and those neutrons can go into the surrounding reactor material and activate it, which is to make it radioactive. But those radioactive elements are not long-lived. So that is why it's a much more desirable thing. Now, again, thinking about the differences between fission and fusion, the fuel for fission is present at all times, and you have to carefully moderate the reactions. And if you don't, you end up getting something like this picture here, which is Chernobyl. None of you will be old enough to remember this. I mean, I was 6 when this happened. This happened in 1985, and it was a really bad nuclear accident because basically people took their eye off the ball. So you really can't do that. Now, in fusion, we have a very small amount of fuel present at any given time, and it's really easy to just turn the reactor off and it stopped working. It's really easy to make fusion not work. We've been doing that for the last few decades, right? So we know that it doesn't take much for fusion to stop working, so it's inherently safe. You won't get these meltdown situations. And last but not least, it doesn't produce carbon, and that's the one thing we need for a sustainable energy source going into the future, is that we're not adding carbon into the atmosphere, and so we're not contributing further to climate change. This is something that we need to address. Now, of course, fusion is not going to address this sort of near-term problem that we need to fix with the energy sources we have now, but what it will do is create a very nice long-term solution to our future in terms of carbon-free energy sources. So that's why we've chosen to work on this for such a long time, because it's extremely attractive. Now, let's get to the crux of this. How on earth do you make fusion work? In order to make this little star in a jar, this star in a box on Earth, we have to be able to heat and hold together matter at 150 million degrees Kelvin. So we need this matter to be 150 million degrees, but we need to hold it together so the particles will fuse without touching it. That sounds really, really difficult to do, doesn't it? Now, the sun and the stars, it's easy for them. They're massive, so they use their own gravitational field to keep them together. But we don't have a lamp the size of the star on Earth, so we can't do that. So we have to be a bit smarter in order to make this happen on Earth. Now, something really interesting happens to matter when we start heating it to those kind of temperatures. So if you know from your school education, you know there are solids, liquids, and gases. Well, there are in fact 6 states of matter, not just 3. But I'm not going to talk about the other 2. What I will talk to you about is the 4th state of matter, which is called plasma. And what happens is, when you add energy to an atom, eventually the electrons that are kind of whizzing around the nucleus can escape. And what you're left with is a kind of soup of charged particles. So the positively charged middle bits, the ions, nuclei, swimming around, and then the negatively charged electrons. And that soup of charged particles is this plasma. And plasma actually makes up 99.99999% of the visible universe. Of course, we don't know what's happening with the stuff we can't see, but with the visible universe, most of it is plasma. So we are pretty lucky to be solids, liquids, and gases, because most of this universe that we live in, that we can see, is made of plasma. And so hence why I'm a plasma physicist, is I need to understand how to deal with plasma in order to make fusion happen. So what is the crux of fusion? How do we make it happen? So there are three little knobs that we have to twiddle in order to get fusion to work. So there are three things that we need to consider: the temperature, so it has to be pretty hot, the density of particles that are in there, and then how long you can confine it together for, where you're getting net energy. So we call that the energy confinement time. Now, of course, temperature is basically non-negotiable. You need to get these particles together. Now, you've got these two particles there, both positively charged, and when you try to bring them together, they resist each other. It's called the Coulomb repulsion. And in order to overcome that, you have to heat fuel to really high temperatures. So the temperature part is pretty much, you can play around with a little bit, but it's really not the thing that you can twiddle. So there are two approaches then. So we can keep a moderate density of particles together for a long time, or we can do something like an extremely dense amount of particles together for a very short time, but then just do it over and over again, okay? Now, what does that look like in reality? So there are two main approaches. So there's inertial confinement, which involves giant lasers, so hence that's what I do. And then there's something called magnetic confinement. So let me talk about magnetic confinement first. So if you think about what I said a plasma was, it's basically made up of a bunch of charged particles. And what charged particles love to do is travel along magnetic field lines. And so what you can do is you can make a magnetic bottle. And so what you see here is a magnetic donut called a tokamak. That's a Russian acronym, which I don't know because I don't speak Russian. And this particular tokamak that you can see here is called the Joint European Torus. And that is here in the UK. It's down in Oxfordshire. And it's the most successful fusion project to date. So it's a really exciting thing to have here in the UK. It's run by this body called Eurofusion, because it's a European project. And so what happens is there are specially shaped magnetic fields which follow around the kind of dimensions of this device, which you end up with a kind of helical magnetic field that goes all the way around the center of the donut. And the particles, the charged particles inside this donut, just want to follow those lines and not touch the walls. Because if they fly out and touch the walls, basically then the whole thing cools down and no fusion can occur. And also there will be significant damage to the reactor walls as well. So magnetic confinement is basically that approach of keeping a kind of moderate density of particles together for a long period of time. Now, if you remember rightly, I said there was another sort of fusion, which is keeping a very dense amount of particles together for a very short period of time. And that is what we do here with inertial confinement. So we take maybe 200 of the world's most powerful lasers, and we crush the hell out of a tiny little ball-bearing sized pellet of deuterium and tritium. We compress it to very, very high densities until it kind of basically self-ignites. That's sort of like a diesel engine, you know, where you compress the fuel until it self-ignites. And so basically so you're confining the fuel essentially with its own inertia, right? And then you do this over and over again. So it's kind of like a fusion diesel engine essentially, where you're just doing this over and over again so that you get that energy. So that's kind of the rough two ways in which fusion can be done. There are lots of variations on the theme, but they largely fall into these kind of two categories. Now, suppose we were to get this, you know, fusion device to work, whatever it is, whether it's a tokamak as can be seen here, or whether it's lasers. How do you get the energy out? It's not really clear, is it? So what happens? So, well, we've got this plasma in the center here burning away, producing fusion energy, and then these neutrons come out. Now, in the surrounding reactor, we have our lithium, which is what we said we needed to make tritium. So the neutrons will come out and interact with the lithium, turn into tritium, but also something else happens. And that is the lithium gets hot, and then we heat water, and then we make steam, and then we drive turbines. So it's a depressingly Victorian back end to what is a rather space age front end. But it's a really good way of getting energy out, and that's how we know how. So let's not change too many things at once. You know, it's got this sort of super space age way of generating energy. Nothing wrong with a gas turbine, right? Let's use that. So that's how it would basically work. So where are we? Well, I'm not going to talk specifically about lasers at this point, although the device I showed you is called the National Ignition Facility, and it's a really exciting device that is getting quite close to getting their energy, maybe a few years away. It's kind of exciting to be part of that. But the tokamak kind of area is a little bit ahead in terms of producing net energy, although trying to compare the two is a bit like trying to compare apples and oranges, to be honest. So this cartoon here is the jet device that we have, which I talked about at the moment. Now, in the south of France, so Aneeqa will talk about this a lot more, but there's this device called ITER being built in the south of France. Physicists aren't stupid, they like sunny holidays, so it's a really nice place to be. Now, this is the next step device. It's much, much bigger, should produce net energy, and there should be first light in this device in around 2025. So really exciting times because it's really coming up quite soon. And then beyond that, we need a demonstration reactor, which is, at the moment, the plans are called DEMO, imaginatively. But in order to move from here to here, we've had to involve a huge amount of industry that are used to building things like nuclear submarines and heavy engineering and bridges and all sorts of things like that. So we're basically sort of almost passing the baton over to these commercial companies. Obviously, we still need to understand the science. ITER at the moment is very much a science project. This is where we are. But we really need a new generation of engineers and scientists that are trained in the right skills. So hopefully some of you will see this and get excited and come and join us on this fusion mission, because there's still years of work left to do. So on that note, thank you so much, and I'll stop talking.
Thank you very much, Kate. So I've got a ton of questions for you. As our listeners will see, I've marked a number of these as some that I will attempt to get Kate to answer. There are probably too many, and there are plenty of additional questions that have been submitted as well. If we don't get through all of them, which we probably won't, we'll try to give you some answers during the week as well. Yeah. And of course, the material during the week will also perhaps answer some of those questions.
Absolutely. Now, students will be able to answer those questions too.
So we do also have a forum, as you indicate. So I wanted to perhaps take a step back first, and both Omer and Josh asked questions in the area of what are the advantages that we actually are missing in order to make this happen, and so in a sense, what are the limiting factors in making fusion work? So that's
right. So that's a really quite tricky question, but let's look at magnetic confinement at the moment. So at the moment, JET, for example, is a very successful device. Back in 1997, it produced about 16 megawatts of fusion power. Now, if you think about what a classic power station is, it's kind of on the gigawatt level, 1 to 3 gigawatts, something like that. So the problem is that fusion power was only produced for a couple of seconds. And this is because tokamaks are inherently unstable. They've got sort of turbulent transport inside them. And in order to overcome that, you have to go bigger. You have to, unfortunately, make a bigger reactor, which is what ITER is. So at the moment, we're trying to figure out how to make a reactor of that size, which obviously they've done a good job of doing, because it's almost built, right? It's very exciting times. If you go on the ITER website, you can see the progress in the gallery of where they've got to. So we're trying to get to a situation where we can make a plasma the aim is about 400 seconds at the moment, to get net energy, which we've never done before, to understand how that works, how those plasmas work, because they are in a different regime to what we're used to operating in. So there's a bunch of science that needs to be done. on these kind of reactors of this scale, which we've never had to do before. And one of the key problems with that is you have to back a horse before you know the horse is the winner. Otherwise, you're never going to build something of that size. So it's what we call technology down select before you even know if that is the right technology. So that's when you're talking about big scale fusion like that, that's the main issue. And I think that's what's driven a lot of small private companies to actually try and create smaller tokamaks. Now, these tokamaks are the ITER, they're sort of like a big donut shape, but these smaller companies are now making these kind of chord apple shaped ones, because there are two approaches. You can make it bigger or you can make the magnetic field bigger. We now have the technology to do that, which we didn't back in the day. So now things are sort of moving on. It's quite interesting. Then there are other things. Sorry, I'm talking a lot here, but then there are other things to consider, like materials, which is what Aneeqa's going to talk about. That could be a real showstopper if we don't get the right materials to make the box out of to contain this miniature star, because there's it is most extreme conditions on Earth.
So yeah, we've already got some questions coming in on the materials. I think I'll be pushing those to Aneeqa later. In relation to the turbulence you mentioned, Charlotte is asking about the instabilities in magnetic fields and so on. Is that related to the turbulence that you're talking about for the plasmas?
Yeah. So there's also, they're all kind of tricky to get into, and also I'm not a magnetic confinement person. I'm a laser plasma person. But yeah, there's lots of interaction between magnetic fields and the particles in there, and the currents flowing in there, which make these things unstable. So I like to think of plasmas as a kind of stroppy teenager of the states of matter world. Basically, they very rarely work in your favor, and you try to tell them to do something and they do the complete opposite. So it's very, very difficult to kind of try and have patience as a plasma physicist, because they're very interesting things to deal with. Now, that's not saying that laser plasma, laser-driven fusion is any better. It's not. We have our own set of instabilities which act to destroy things. So we're not getting off scot-free here. We've got some serious problems as well.
Okay, so you mentioned about the aspect about perhaps having to back a horse before you know that it wins. One of the questions that David is asking is whether you have an opinion on the options between tokamaks and stellarators.
That's really interesting. Right, so if you've never seen a stellarator, I
haven't.
So you all need to Google Wendelstein 7X. And we can give you that. We can put a link somewhere.
Yeah.
If you like engineering, it is one of the most phenomenally beautiful things that I've ever seen, right? So there are two different approaches to shaping the magnetic field to confine the field. You either create a helical field in the center using like toroidal and colloidal field coils like in a tokamak, or you make these crazy field structures that kind of rotate around, and it's the field, it's the coils that you make the field with that you make crazy, let's say, rather than using simple coils to make a crazy field, if that makes sense, right? Either way, right? You're talking to someone who's quite agnostic, actually, because even though I am a laser plasma person, my personal feelings are that I just want fusion to work, right? And every single type of fusion has its own issues and has its own problems and has its own wicked physics problems and wicked engineering problems that need solving in order to make them work. So there isn't a particular route where you can look at and go, yes, that one, because it's hard, right? They all have their own problems. So even though I absolutely love firing lasers at things, and I would love to say, yes, of course, lasers, blah, blah, blah. The bottom line is they're all difficult to do. Now, the bigger it gets, the harder it gets, because that requires cash. And so, the bigger these devices are, the more will you have to have and the better the science is in order to justify building it. So there are sort of more practical political issues to be considered rather than just the physics, actually.
Okay. Well, thank you for this, Kate. We might get back to you later on as well on the big physics. I know there's also been a lot of questions on actually the type of fusion fuel that you use, and I'll see if we can perhaps go into some detail about that on our website later. But for now, thank you so much, Kate, and we'll get back to you a bit later.
Thank you.
So if you have any questions for Kate, do feel free to let them come in. We will record your questions, make a note of them, even if we don't get to answer them, and we'll try to answer as many questions as possible later. With that said, for now, let's invite and welcome Dr. Aneeqa Khan. Aneeqa is a research fellow in engineering, so actually someone who knows how to build stuff, as opposed to me, who just knows how to talk about stuff, I think. Aneeqa works in engineering at University of Manchester, and she's focused on understanding the different properties of materials, how they could work in fusion, and how they react to radiation. So let's just see if we have Aneeqa online. Yeah, welcome, Aneeqa. Good to see you.
Good to see you.
Yeah. So Aneeqa, thank you firstly for joining our masterclass here. And before we get a bit more into your research, so how did you get into engineering?
So I think a bit like Kate as well, actually. It was a bit of an accident. So when I was in college, I actually really wanted to do geography, but I ended up missing like a page in my A-level exam. And so then that was the end of my geography career. And I really liked maths and science, and I thought engineering was kind of a combination of them. And yeah, that's how I got into engineering.
Okay, yeah, thank you. No, it's great for me to talk to a proper engineer. So in nuclear physics, of course, we have to work with engineering, but we mostly just dabble in it and let the professionals do the proper jobs, I think it's fair to say. So it's great to see you here. And as I said before, we've already had plenty of questions come in on the material. So I look forward to hearing that. I think we should go straight into your presentation and then come back with some questions subsequently. So over to you. Thank you, Aneeqa.
Okay, sounds good. So as Christian said, I'm going to be talking about materials for nuclear fusion. So I'm just going to start off with what Kate mentioned before about the fusion reaction. So as Kate mentioned, the fusion reaction that we're going to be using when we're trying to kind of get nuclear power going is the deuterium-tritium reaction. And we use this specific reaction because it's got a greater cross-section than other fusion reactions within a similar energy range. So that just means that reaction is more likely to occur, actually 100 times more likely to occur. So the deuterium and tritium react together to produce helium and neutrons. The really key thing that I want everyone to kind of pick up on is that it's very high energy neutrons. These energies of 14 MeV are kind of a big issue for material scientists and engineers because they're very different to the energy profile of neutrons produced in fission reactions, and they can cause a lot of other types of damage. And then also we have energetic helium, which is produced as well, which is something that we also have to consider as engineers and material scientists. So as Kate mentioned, ITER is the biggest experimental reactor that's currently been built in the south of France, and that's somewhere where I used to work actually a few years ago, and I really miss the weather there now living in Manchester. And as you can kind of see, it's just a huge site, and it's a massive international project. So I think this is one of the exciting things about working in science and working in fusion. So ITER is like a collaboration between the European Union, America, China, Russia, Korea, Japan, and India, I think. And then they're the official partners, but then there's other countries that work in through other ways or through contracts as well. So it's just a huge international project, and it's really exciting to be able to work on such a big site with people from all over the world. So just for a bit of a kind of idea of the scale. So I don't know if you can see this kind of little man in the bottom right-hand corner. to show how big it is. And the radius of the tokamak itself is around 6 meters with a diameter of 28.6 meters. So it's absolutely massive. It's a lot bigger than JET, which is the current largest operating reactor. So building such a big reactor obviously has a lot of challenges. So what are the materials issues for fusion reactors? So as I mentioned before, you've got 14 MeV neutrons. So these neutrons will cause a lot of damage and they're very high energy. So that's one of the key issues that we have to look at. Another one is that there's very high heat loads. As Kate mentioned, the temperatures in the center of the plasma are 150 million degrees. That won't be the same at the edge of the reactor, but it's still very, very hot. We've also mentioned previously that we don't want to produce kind of radioactive waste or high-level radioactive waste, as the case with fission reactors. So we could, obviously we don't have the radioactive fuels in the same way as a fission reactor, but as Kate mentioned, we can get activation of the materials that the reactor is made from. So we have to be really careful to choose materials that won't go through this kind of activation to the extent that we would have high-level waste. Another thing which is kind of really important, as I mentioned before, is the helium that's produced. That can cause a lot of damage in the reactor as well. So that's another thing we have to consider. Then we also have the effects of the plasma itself, which includes helium, but also other gases like the hydrogen isotopes as well. So kind of the effect of the plasma with the materials in the reactor is such an important part of fusion materials research at the moment. And then we also have really high magnetic fields. Obviously, Kate's from a laser background, but I'm working, or ITER is a magnetically confined reactor. So we're really keen to look at what is the impact of the magnetic fields on the materials used for the reactor, but also to generate those fields, you need really special materials and special environments as well. So let's go into a bit more detail into all of these kind of issues. So we've got the 14 MeV neutrons. You don't need to worry too much about all the different terminology, but essentially when a neutron will kind of hit your material, like a snooker ball hitting the other snooker balls, don't know what, there's a different name for all of them, you kind of get like a knock-on reaction. And this causes damage in the material. So it causes atoms to be displaced within the lattice of the material. And it can also cause materials to change into other atoms. So that's called transmutation, and that's what leads to activation of the materials as well, because you can generate radioactive isotopes as an example, but you can also generate stuff like helium, which can cause further damage within your materials. Now, the damage generated by neutrons varies with the time scale and the length scale that you're looking at. So there's a huge amount of research going on across all of these timescales and length scales to try and really get to the bottom of how these materials will behave, what will be the impact of the 14 MeV neutrons. Unfortunately, we don't have a 14 MeV neutron source that we can use to look at all of those issues. So people use different types of modeling on computers at small scales and large scales to try and model this, but also we look at other ways of trying to surrogate this damage. So one way is that people might use ions, which they fire at the material. So if you imagine when your neutron hits the material, an atom will be displaced and that atom will hit other atoms. So we can bypass the neutron and kind of just fire the atoms themselves at the material. So as I'll go talk about tungsten a bit later, that's what I've been working on kind of recently. So people would fire tungsten atoms at tungsten and try and recreate the displacement damage and use different like diagnostic techniques to see how it would behave. You can also fire other types of atoms, such as protons or helium, to kind of recreate this damage created by the neutrons. But it's a huge area of research that's going on at the moment. Then if we talk about the high heat loads, so I just wanted to put this in perspective because the heat loads are just crazy. So if you've got HWR nuclear reactors, this is a re-entry vehicle, this is a Rolls-Royce Trent engine, and this is a component of the ITER reactor called the diverter, which I'll talk about towards the end of the talk. And during steady state, that's already going to be like steady state operations of the reactor. That's going to be facing kind of higher heat loads than all three of those previous engineering projects. Then also, as Kate mentioned, you get like instabilities in the plasma and stuff, and that can lead to kind of transient events or just sudden kind of extremely high heat loads, which, you know, we're looking here at 2000 megawatts per meter squared. And that's, you know, an order of magnitude more than a rocket or arc welding, for example. So really extreme environments. So being able to, again, see how materials cope under those high heat loads and being able to operate and both contain the plasma and also not influence the plasma or cause the plasma to turn off as well are kind of things that are really important and that we have to look at. I also mentioned we want reduced activation materials. So there's been a lot of modeling work that's gone into, you know, finding out which atoms and which isotopes will transmutate to other ones. And so for different parts of the reactor, we can use different types of material, because in different regions, you'll have different levels of neutrons and different amounts of shielding as well, which will kind of slow the energy of the neutrons too. So in different areas, we want to use different materials. But the key thing is we want to stick to, we don't want to use anything that would be orange, basically, in certain areas of the reactor, because then we will generate kind of waste, which is, you know, a key thing that we don't want. This is just in another area of the reactor, in the kind of blanket area, which again I'll mention, where you have a bit more of an option, fewer orange elements essentially. Now if we talk about the helium, so helium will have an impact because it's both present in the plasma, but as I mentioned before, it's also something that can be produced by transmutation from the neutrons kind of hitting your material as well. Depending what your material is, that can have different influences. Again, I'm going to talk about tungsten because I love tungsten. But depending on the temperature of the exposure and the energy of that helium that's impacting your tungsten, that can cause a series of different types of surface modification. So at lower temperatures of 600 to 700 Kelvin, you can get nanobubbles in the surface of your sample. Slightly higher temperatures, 900 to 1900 Kelvin, you get this really cool surface modification, which is called fuzz. And it turns the surface of your tungsten black, because you've got all these little pores and like these little tendrils forming on the surface. And it's very cool. But it could be an issue during operation of a fusion reactor, because if that breaks off, that could produce dust, which could impact the performance of the plasma, which is something, you know, we don't want to happen. So we really need to understand that. And then you've got at very high temperatures, large voids forming in the tungsten as well. And this can all impact the thermal properties of the tungsten, mechanical properties, and whether it will have fuel retention or not. So as Kate mentioned, we're using tritium. Tritium is a radioactive element, and it's very highly controlled. And we're only allowed to have certain amounts of tritium on site when we're operating a machine like ITER. So we need to make sure that we're not, we don't have retention of the fuel within our materials, because that's going to contribute towards the inventory of the tritium. So we want to try and minimize that, and for safety reasons as well. We don't want to keep that in the like locked into the material. So that's something we have to really consider and be very careful about. Then if we move on to the effects of the plasma itself, so as I mentioned, you could have erosion of the different materials. Materials can get eroded and then be transported in the plasma along those complicated magnetic field lines and be deposited somewhere else. There can be dust produced, as I mentioned before, fuel retention. You can get bubbles, you can get blisters. You can get embrittlement of the material, which can be an issue as well, because, you know, stuff can break off or stop working properly or break. And these are all things that we want to try to avoid. So it's really important that we understand the interaction between the plasma itself and the materials. And then I mentioned the magnetic fields. So we do need to consider what materials we'd use to get the superconducting magnetic fields. So for ITER, for example, the maximum field in the center of the central solenoid will have an intensity of 13 Teslas, which is just massive. If you can compare that to like a PET scanner in a hospital, which is typically around 1.5 Teslas, which is already very high. So yeah, working with generating really high magnetic fields is a very big challenge for material scientists. And additionally, what is the impact of having such a strong magnetic field on the other materials in your reactor? That's also something that people are looking into and have to consider. But I think the key takeaway is that you have to kind of look at the combination of all these different effects on the materials. And it's very challenging when we don't have a large scale reactor built. So we have to kind of try and combine them in small scale lab experiments or larger kind of collaborative experiments to try and predict how they behave, and then also using modeling work to fill in the gaps as well. And one really exciting thing that's kind of kicking off at the moment is something called in silico in silico modeling, which is basically when you just make a virtual experiment to see how different materials will behave. And going forward with the increase in artificial intelligence as well, this is a really key area of research for material scientists as well, this in silico modeling. So I'm just going to kind of finish off the presentation looking at the materials that we would use in ITER that have been selected. So we have the cryostat, which is highlighted in green, which is basically like a giant fridge, essentially. So that's going to keep everything cool, keep the magnets cool, and that's going to be made of stainless steel. And then you have the vacuum vessel, which again is kind of like another kind of protective area, keeps everything under vacuum so it can operate, and that's also going to be made of stainless steel as well. Then we have the diverter, which I mentioned previously, and the diverter is kind of just like an exhaust for the reactor. It collects like dust and ash and kind of cleans it out, from the reactor. And it's been decided for ITER that tungsten is going to be used for that purpose, because this area is going to be experiencing the highest heat loads of any of the kind of plasma facing components of the reactor, and tungsten has got the highest melting point of any of the metals. So that's why we've gone for using tungsten in that area. Then we've got the blanket, which is this red area here, and that's going to be made from beryllium, both because it doesn't really impact the plasma too much, but also it's what was I going to say? It's got good properties basically to stop the neutrons as well, and it doesn't retain fuel, which is a key issue that I mentioned previously. Another really cool thing about ITER specifically is, so as Kate mentioned before, we want to try and breed tritium in a fusion reactor. We want to produce more of the fuel while we're operating. So far, all the experimental tokamaks that have existed haven't been able to do that. We use tritium from other sources. So later on during ITER's operation, they're going to exchange some of the little modules of the blanket and use different test modules to kind of see how we can breed the tritium effectively. So that's going to be a really exciting step for fusion, proving that we can breed tritium in the reactor while it's operating, and it's going to look a lot of different concepts to see how that would work in practice. So that's a really exciting kind of thing that's going to be happening in ITER. And then finally, we've got the superconducting magnets. So they will be made of niobium tin or niobium titanium. And I think one key thing to look at here is that they're going to be super cooled. So the temperatures around the magnet are going to be almost absolute zero. And then in the center of your plasma, you're going to have temperatures of like 150 million degrees. So nowhere else in the universe do you have that temperature gradient going from almost absolute zero to 10 times hotter than the center of the sun in the space of 6 meters. It's a bit crazy when you think about it. But it just highlights how big an engineering challenge this reactor is, but also something so exciting to work on and something that's never been done before. So that's me. That's the end of the talk. So I'll pass it back to Christian.
Okay, so thank you very much, Aneeqa. That's fantastic to see. And so leading on from this, actually, particularly perhaps the last bit you say, there was a question I think from Jimmy that encapsulates this a lot. How much of the technology that goes into building ITER is really prototype tech?
I think a lot. I can't give you a percentage, but most of it has been specially developed for this process, and it's really driven a lot of innovation, and kind of whole industries have been set up to be able to have a supply chain that can do all of this stuff. And because it is an international project, it's kind of what's the word? Kickstarting industry in all of the partner countries. So it might be you'll be getting magnets from Korea, but also in Japan they might be making the same component but in a slightly different way, which obviously adds complexity in trying to fit things together, but it's also generating a huge amount of innovation that has just been kind of for this project.
So more or less all of it, in a sense, apart from the walls in itself of the building.
Yeah, basically.
So, okay, no, I mean that's great to hear. So I think that leads to some degree into one of the next questions, which is triggered, I think, by particularly Clara's question on whether and how this could be used as a sustainable energy source. I think I might add, and on which timescale do you think that is? I know it's hard to predict, okay, but is it realistic? Do you think? What are your thoughts on this? Will it happen?
So there's always this question with fusion power: when's it going to happen? And there's a joke that everyone always says it's 50 years in the future whenever you ask them. But I think now we're really seeing a turning point. So not only do we have ITER, which is set to come online, I think in 2025, so just 5 years away is when it's going to have its first plasma. But also in the UK, we've got the STEP program, which is just starting now, where they want to also develop kind of a spherical tokamak for energy production. And also we're seeing huge amounts of industry. As Kate mentioned, there's a lot of companies that are starting to really take off. So you've got companies like General Fusion or Tokamak Energy within the UK as well. And recently this year, there's also been a launch of a fusion industry association, and this is something that I've not seen before. So I think with the influence of industry, I think we are a lot closer to seeing fusion becoming a reality. Okay,
now that's exciting to hear, because it means that we might even be talking about our work life kind of timescales rather than well into our end of my life, for example, right?
Yeah.
So that's great to hear. So there's a question from Louise, which I think is actually about this technology and how you can control it, because she's asking about what is actually, in your view, the most damaging aspect to the reactor vessel. Is it helium? Is it the plasma? You might add, is it the neutrons? What's actually the most difficult to handle from your perspective?
I think it's a combined. It's really the synergistic effects of all of them. Really, is all of them have really big challenges associated with them. I think at the moment in labs that we have, we can recreate the plasmas and the helium plasmas, and we can recreate high temperatures, but we don't have that 14 MeV neutron source. So I'd say that's the biggest thing that we need to work on at the moment.
Okay, yeah, thank you. So you mentioned this aspect about tritium breeding as well, and how you see that as transformational. Can you perhaps elaborate on that? There were some questions also about the challenges of extracting tritium, and is that an environmental issue, and so on. What's your view on that in the context of tritium in your type of reactor in ITER, for example?
So yeah, I think this is definitely new, again, very innovative, very new technology. It's something that's not been done before, especially during the operation of a reactor. And at the moment, most of the tritium, I think it comes from CANDU reactors in Canada, I believe. I might be wrong on that one. But there's a very limited supply on Earth. So to be able to, and although we don't need a lot, if we want this to be a sustainable form of technology and a sustainable form of energy in the future, we have to be able to breed it within the reactor to make sure that's a reality. So yeah, I think this is going to be very challenging, but very important moving forward.
Okay. So I know there's been plenty of other questions, and also some that I haven't been able to mark yet as potentially answered, but we'll get back to many of them later. I can reassure everyone. But there was one question from Ella that I picked out. I don't know if you have an opinion on it, but do you have an opinion on the prospect for what you might call self-healing liquid metals in relation to fusion reactors? Is there any prospect of that?
Yeah, so as Kate mentioned, Eurofusion, they are running JET at the moment, and they have a lot of tasks for the development of a demonstration reactor, which was the large reactor which Kate mentioned. And one of their work packages is exactly to look at this kind of liquid metal walls. So there's definitely a big, buzz about it, and I think it's a very exciting form of technology. But obviously, the technology readiness level is not at the same as other concepts, but very exciting.
Okay. No, that's very interesting to hear. It's also interesting, yeah, from my perspective. I've seen liquid metal targets being used at CERN, where they bombarded with a massive proton beam, and the problem is that it starts slushing inside the target, but from the impact of the beam. But thank you so much, Aneeqa. I think I'd like to invite Kate also to join us back, because there are some questions. There's been quite a lot of questions lately to I think both of you in relation to this aspect about big facilities. So you've talked about ITER. Kate, you've talked about massive laser facilities, and I thought we should perhaps end by asking you both to, what do you think? What's it actually like to work at these facilities?
Okay,
maybe Kate first. We haven't heard from you for a little while.
So, I mean, I'm going to confess to you that 30% of why I went into physics is because I knew I would get to travel the world, right? And that has played out. And one of the things about the fact that, you know, you can't just go up the road and there be a big laser there. I mean, of course, I'm very lucky that 3.5 hours drive, there is one of the world's most powerful lasers at the Rutherford Appleton Laboratory. I grew up on that laser. That's where I did my PhD, and most of my research has been done there. But I've also been able to go all around the world, working in different laboratories in different countries. I've been to the US and Japan, and I've currently got a collaboration with a group in Pisa with a wonderful laser there. And I love pasta and pizza. So for me, this is just complete heaven that I get to go and work with some wonderful people and then eat loads of food at the same time, because that's my top priority, really. But I worked at the Rutherford Appleton Laboratory for 10.5 years before coming to York. And no matter how hard it got, whenever you come into that site in a car and a bus and you see it just getting nearer and nearer, and all of these beautiful big physics facilities, and you just think, you have to pinch yourself. I just think, how on earth did me, this person from Ashford, who, you know, is no one, end up like working in a place like that with thousands of people who all have very similar goals and similar dreams and similar interests to you, you know, in terms of physics. That is, obviously, there's a broad spectrum of people on site and stuff, but just to be part of something like that and the privilege of that, I still can't believe that I do this stuff. I really can't. Like, it is I mean, you know, and sometimes you have to use that when times get hard and you're in the lab at midnight and things aren't going well and you're sort of on the verge of tears and you're thinking, this is not going good. And then sometimes you just have to step back and go, yeah, no, this is still one of the biggest privileges, you know. Yeah, anyway, that's what it's like.
So how about you, Aneeqa? So I understand you work a lot at Harwell, at the Harwell facility as well.
Yeah. So yeah, I think just to echo Kate's like feeling of it just being such a huge privilege, because when you work at these big science experiments, whether it's ITER, whether it's Harwell, you're just with world leaders in that field, and it's just, you have the opportunity to just learn so much from each other, and you don't get that anywhere else. I feel that you get at such like big science experiments. So it's just both for yourself to learn like professionally, but also it's just really exciting and really cool because that kit is so state of the art and you don't get that anywhere else. So yeah, I think it's just a really cool experience.
Okay, thank you so much. I think that's a fantastic note to end on. So thank you to both of you for sharing your experience with these big facilities and with the science of what's underneath it all, under the hood of ITER and Harwell and the Central Laser Facility and other cool places around the world. So with that, we'll finish for today, and everyone will be able to find more material on the website with activities and quizzes that focus on these aspects of why is it that fusion energy might be needed and how do we actually do it. So with that, thanks for now, and we'll see you again next week, and do engage with the forum during the week. And thanks to Kate and Aneeqa.